Hello my friends, and welcome back to KrossUSA. Today we're taking you inside some of the world's most sophisticated wheel manufacturing facilities. From elastic railway wheels to high-performance race car rims, we'll explore the cutting-edge technologies that keep our world rolling. Let's dive in. First up, we're visiting Railteco, where they've revolutionized urban rail transport with their elastic wheel technology. These aren't your grandfather's train wheels. They're engineering masterpieces that combine comfort, durability, and noise reduction in ways that seemed impossible just decades ago. What makes these wheels special? Traditional solid wheels create vibration and noise that can be felt throughout entire train cars. Railteco's elastic wheels feature a rubber-steel composite design that acts like a shock absorber. The secret lies in their patented vulcanization process, where rubber compounds are chemically bonded to precision-machined steel hubs under extreme heat and pressure. We're talking 180 degrees Celsius and 150 bars of pressure. The production begins with high-grade steel blanks that undergo CNC precision, turning on massive lathes. These machines can hold tolerances within 0.05 millimeters. That's thinner than a human hair. Next comes the critical rubber preparation phase. Special compounds including natural rubber, carbon black, and proprietary additives are mixed in computer-controlled Banbury mixers. NTHE magic happens in their custom-built vulcanization presses. Each wheel spends exactly 45 minutes under controlled temperature and pressure, while the rubber chemically bonds with the steel at a molecular level. Quality control is extraordinary. Every wheel undergoes dynamic balancing tests, resonance frequency analysis, and fatigue testing that simulates 2 million kilometers of service life. Know the result? Wheels that reduce track wear by 40%, cut noise pollution by up to 10 decibels, and provide smoother rides for millions of passengers daily. It's remarkable how this seemingly simple innovation transforms the entire urban transit experience. Now let's explore Railteco's incredible wheel assembly press system, a hydraulic powerhouse that can generate up to 2,000 tons of force with surgical precision. This isn't just about brute strength, it's about controlled, measurable force application that ensures perfect wheel-to-axle fits every single time. This massive machine stands 12 feet tall and weighs 25 tons, but watch how smoothly it operates. The hydraulic system uses servo-controlled pumps that can modulate pressure in real time. The pressing chamber features laser positioning systems that ensure components are aligned within 0.02 millimeters before pressing begins. What's fascinating is the force monitoring capability. The machine continuously measures resistance throughout the pressing cycle. If it detects any anomaly, it immediately stops and alerts operators. The automated handling system can rotate between wheel mounting, brake disc installation, and gear pressing operations without manual reconfiguration. Let's watch a complete cycle. First, the wheel hub is positioned using pneumatic clamps that distribute holding force evenly. The axle, heated to precisely 200 degrees Celsius for thermal expansion, is positioned by robotic arms with 6-axis movement capability. As pressing begins, you'll notice the gradual force application, starting at 50 tons and building to the calculated optimal force, which varies based on the specific wheel-axle combination. The entire process is monitored by load cells that measure force to within 1 ton accuracy. NFOR brake disc mounting. The process requires different parameters entirely. The machine automatically adjusts pressing speed and force based on the component being installed. Temperature sensors ensure thermal conditions remain optimal throughout the operation. But pressing is only half the story. Each assembled wheel set immediately moves to the testing station, where it undergoes comprehensive evaluation. Dynamic balancing occurs at speeds up to 160 kilometers per hour, simulating maximum service conditions. Ultrasonic testing checks the integrity of the press-fit connection, ensuring there are no microscopic gaps or stress concentrations. The final step involves runout measurement using laser interferometry, checking that the assembled wheel rotates with less than 0.1 millimeter deviation from perfect circular motion. This level of precision ensures that every wheel set leaving Rail Teco will perform flawlessly for decades of service. When you're riding a smooth, quiet train, remember the incredible engineering precision that made it possible. Welcome to Vlucon's state-of-the-art facility, where they've mastered the art of steel rim pressing for heavy-duty applications. These aren't lightweight automotive rims. We're talking about industrial-grade steel rims that need to withstand extreme loads, temperatures, and conditions that would destroy conventional wheels. The manufacturing process here combines old-world metallurgy knowledge with cutting-edge automation. Everything starts with premium steel selection. Vlucon uses high-carbon steel billets that undergo rigorous chemical analysis, checking for exact percentages of carbon, manganese, silicon, and trace elements. These billets enter massive induction heating furnaces that can reach 200 degrees Celsius. NTHE heating process is critical. Too fast, and you create internal stresses. Too slow, and you waste energy and time. Vlucon's computerized heating system monitors temperature at 16 different points within each billet, ensuring uniform heat distribution. The entire heating cycle takes 3.5 hours and follows a precisely programmed temperature curve. Now comes the spectacular forging operation. The heated steel moves to a 5,000-ton hydraulic press, one of the largest in Europe. Watch as the ram descends with controlled fury, transforming the glowing billet into a rough wheel shape in just 30 seconds. NBUT, this isn't random hammering. The press follows a computer-programmed sequence that applies force in specific patterns. The first strike creates the basic rim shape. Subsequent operations form the spoke pattern and hub area. Temperature monitoring continues throughout. If the steel cools below 900 degrees, it returns to the furnace for reheating. NTHE forging die itself is a masterpiece of tool engineering. Made from specially treated tool steel, it can withstand thousands of forging cycles while maintaining dimensional accuracy within 2 millimeters. After forging comes precision machining, and this is where Vlucon really shines. The rough forged wheels enter CNC turning centers with 40 horsepower spindles and carbide tooling that can remove metal at incredible rates while maintaining surface finishes measured in micrometers. NTHE machining sequence is fascinating to watch. First, the rim outer diameter is turned to exact specifications. We're talking tolerances of plus or minus 0.1 millimeters on wheels that are over a meter in diameter. Next, The spoke areas are machined using specialized tool paths that ensure optimal material distribution and stress flow. NTHE most critical operation is hub machining. This area must interface perfectly with axles or mounting hardware, so tolerances tighten to plus or minus 0.05 millimeters. The CNC machine uses feedback from laser measurement systems to compensate for tool wear in real time, ensuring consistent accuracy even on the last wheel of a production run. But we're not done yet. These wheels need heat treatment to achieve their final properties. They enter massive quenching furnaces where they're heated to 860 degrees Celsius in controlled atmospheres to prevent oxidation. NTHE quenching process is dramatic. Wheels are rapidly cooled in polymer solutions that extract heat at precisely controlled rates. Cool too fast and the steel becomes brittle, too slow, and you don't achieve necessary hardness. Vlucon's quenching system monitors cooling rates at multiple points and adjusts solution flow and temperature automatically. Tempering follows immediately, a careful reheating to 400 degrees that relieves internal stresses while maintaining strength. The entire heat treatment cycle takes 18 hours and is monitored by computerized systems that can detect and correct deviations instantly. Quality control is exhaustive. Every wheel undergoes magnetic particle inspection to detect microscopic cracks, hardness testing at multiple locations, and dimensional verification using coordinate measuring machines accurate to 5 micrometers. Then extave rims. The finished rims undergo final balancing using computer-controlled machines that can detect imbalances as small as 5 grams. Any necessary corrections are made by precision drilling to remove material exactly where needed. Before shipping, sample wheels from each batch undergo destructive testing, loading them to failure to verify they exceed design requirements by comfortable margins. It's this attention to detail that allows Vlucon wheels to operate reliably in the harshest industrial environments worldwide. At Lucchini RS in Italy, they've been perfecting railway wheel manufacturing for over a century, and their modern facility represents the pinnacle of metallurgical expertise. These wheels will carry high-speed trains at 300 kilometers per hour, so there's absolutely no margin for error in their production process. Lucchini controls their steel production from the very beginning. In their electric arc furnaces, scrap steel is melted at 600 degrees Celsius, while precisely controlled additions of carbon, manganese, and other alloying elements create the exact chemistry required for railway applications. What's remarkable is their secondary refining process. The molten steel undergoes vacuum degassing to remove hydrogen and other impurities that could cause failures years later in service. Ladle metallurgy stations fine-tune the chemistry to incredibly tight specifications, carbon content controlled to within 0.02 percentage points. The molten steel flows into continuous casting machines that produce perfectly round billets 280 millimeters in diameter. These billets immediately enter the rolling mill while still hot, a process called hot charging that saves energy and improves material properties. NTHE rolling mill is a marvel of mechanical engineering. A series of grooved rollers progressively shape the billet into wheel blanks through 12 passes. Each pass reduces diameter while increasing length, and the precise groove geometry ensures uniform material flow and grain structure. Temperature control during rolling is critical. Pyrometers monitor the steel temperature continuously, and water sprays provide controlled cooling between passes. The finished wheel blank emerges at exactly the right temperature for optimal grain structure formation. The wheel blanks enter hydraulic presses, where they're formed into their final wheel profile. This isn't simple compression. The forming dies create complex internal geometry that optimizes stress distribution throughout the wheel structure. Computer-controlled hydraulics ensure consistent forming pressure and duration. The press cycle takes exactly 90 seconds, during which the wheel undergoes multiple forming operations that create the rim, web, and hub sections simultaneously. Heat treatment at Lucchini follows railway industry standards that have evolved over decades of experience. Wheels are heated in walking beam furnaces to 900 degrees Celsius, ensuring uniform temperature throughout their mass. End-controlled cooling follows specific curves designed to create optimal microstructures. The rim area, which contacts the rail, receives different heat treatment than the hub area, which must resist different types of stresses. And final machining occurs on specialized wheel lathes that can maintain concentricity within 0.1 millimeters. These machines use CBN, cubic boron nitride, cutting tools that can maintain sharp cutting edges even when machining the hardened wheel surfaces. Every wheel undergoes ultrasonic testing to detect internal flaws, dimensional inspection using laser measurement systems, and metallographic analysis of sample sections. Only wheels that meet stringent European railway standards leave the facility, ensuring safe operation at high speeds for millions of passengers. Finally, let's visit Aero Race Wheels, where they create the ultimate in high-performance automotive wheels. These wheels need to be incredibly light, yet strong enough to withstand the extreme forces of racing. The manufacturing techniques here push the boundaries of what's possible with aluminum alloy technology. Aero Race Wheels starts with proprietary aluminum alloys that would make aerospace engineers jealous. Their metallurgy lab develops custom compositions using A356 aluminum as a base, but with carefully controlled additions of magnesium, silicon, and rare earth elements. NTHE casting process uses squeeze casting technology, essentially forging while the metal is still liquid. This eliminates porosity and creates grain structures similar to forged components. The squeeze casting machines apply up to 100 tons of pressure while the aluminum solidifies, resulting in densities over 99.5% of theoretical maximum. The casting dies themselves are masterpieces of precision manufacturing. CNC machined from premium tool steel and coated with specialized release agents, these dies can produce wheels with surface finishes so smooth they require minimal machining. End temperature control is absolutely critical. The aluminum is heated to exactly 700 degrees Celsius, hot enough to flow perfectly, but not so hot that it reacts with the die coatings. Infrared thermometers monitor pour temperature to within 5 degrees. NTHE casting cycle is precisely timed. From pour to demolding takes exactly 4 minutes and 30 seconds. During this time, cooling channels in the dies extract heat at controlled rates to ensure optimal grain structure formation throughout the wheel. Post-casting machining is where Aero Race Wheels really demonstrates their expertise. 5-axis CNC machining centers with 30,000 RPM spindles perform operations that were impossible just a decade ago. NTHE spoke pocketing operation alone removes 40% of the cast wheel's weight, while actually increasing structural strength through optimized material distribution. Computer modeling determines exactly where material can be removed and where it must remain for maximum performance. NSUR face finishes achieved are remarkable. Bearing surfaces machined to 0.4 micrometers raw, which is approaching mirror-like quality. These finishes aren't just for appearance. They reduce stress concentrations and improve fatigue life under racing conditions. The T6 heat treatment process transforms the wheel's mechanical properties dramatically. Solution treatment at 540 degrees Celsius dissolves strengthening precipitates into solid solution, followed by controlled quenching and artificial aging. NTHE aging process is where the magic happens. 8 hours at 160 degrees Celsius allows microscopic precipitates to form that increased strength by over 200%. Real-time monitoring ensures precise temperature control throughout the cycle. In-testing is exhaustive and includes fatigue testing to 10 million cycles, impact testing that exceeds DOT requirements by 50%, and dynamic balancing to tolerances that rival Formula One specifications.